we're going to use Gauss's law to find the electric field around an infinite line of charge. So here is my wire or line going up and down to plus and minus infinity. And I'm going to assume that there are lambda coulombs per metre distributed over the surface of that wire. Now, to use Gauss's law, we have to make a symmetry argument about the form of the electric field. And there are two things that we can deduce just by looking at the problem. The first is if we think about the transverse plane to the wire, then the electric field must be radiating out radially in that direction. The reason is that if the electric field were tilted, we'd be able to distinguish the top from the bottom of the wire, and that's not present in the problem. So E is in the r hat direction. The second thing we can say is that there will be no dependence in E on where I am up and down the length of the string, call that, say, the Z direction, nor on the angle around the string. Because if either of those were true, I could tell the top from the bottom, or I could tell when I was on this side relative to on that side. And again, that information isn't present in the problem. So the magnitude of E is just a function of R. Now we have to choose a Gaussian surface to do the calculation with. And a sensible one to choose is a cylinder around the wire, like so. And we'll make it of radius r and of length l. The reason that's a good choice is twofold. So let's imagine that we're going to actually now calculate, so we'll put that as a cylinder, and then we're going to integrate E dot dA over the cylinder in order to calculate the flux. So let's see why this was a good choice of Gaussian surface. Well, first of all, if I think about the top and the bottom area elements, their vector is pointed upwards or on the bottom downwards, and that's perpendicular to the electric field. So the dot product is 0 for the top and the bottom. If I think about little dA elements on the surface of the cylinder, then their vector is also going to be pointing in the r hat direction, the same direction as the electric field. So the dot product between the electric field and the area around the cylinder will just give me a cosine of 0, which is 1. And so what I get is E of r, that will be the same everywhere on the surface of the cylinder, times the sum over those delta A pieces. And when I add those up, I just get the surface of the cylinder, which is 2 pi r, the distance round, times the height L. So now we can solve using Gauss's law, which says that the flux is equal to the Q enclosed over epsilon 0. And Q enclosed is just the charge on the piece of string within the Gaussian surface. So that's going to be given by lambda, the number of coulombs per metre, times the length. And then we divide by epsilon 0. And so we learn that E of r is lambda over 2 pi epsilon naught r. That is to say that the electric field is given by lambda over 2 pi epsilon naught r hat.